will look at the effects on bone, muscle, the immune system, tendon, brain, microbiota, metabolism, cardiovascular system, and behavior. It involves several groups. Our group in Saint-Étienne, the group led by Angèle Chopard in Montpellier, University of Bordeaux, and Institute in Bordeaux, the Institute of Lorraine, and other groups as well. The first part of this project is with the positive impact of pre-unloading training on the skeleton. The model we use is a mouse model, so it's a preclinical model in which the animals are suspended by their tail so that their posterior legs are unloaded mechanically. And in a second part, we will evaluate the effect of a combination of more training, where the training is done before the suspension, but also during the suspension, so before the phase of mechanical unloading, as well as during the phase of mechanical unloading, combined with nutritional supplements. And I will specifically concentrate on the effects on bone and a little bit on muscle today. The idea is, in the long term, to apply what we learn for the prevention of musculoskeletal and other systems deconditioning in space. So this is our system. These are the mice as they are unloaded and suspended by their tail. We can put, sorry. I think it's this, yes. We can place two animals in a cage so that they are not in isolation, and that's better from the ethical and well-being of the animal. And the protocol consists in an acclimatization phase that is followed by what we call the pre-unloading training phase. So it's 3 weeks when the animals do some physical exercise. You have seen a preview of that because of my mistake. And then for 3 weeks, the animal will be mechanically unloaded. There is a control group that will not do any special exercise and a group that will do the training. And we can recover samples just before the mechanical unloading, after a week of mechanical unloading, so short period, and after 3 weeks of mechanical unloading. The physical exercise that these animals do is a combination of endurance and resistive training. The endurance is a rodent treadmill. And the idea is to really push these animals to the maximum by successive trainings and successive repetitions of this type of exercise. And in terms of resistant training, we don't make them lift weights, but we make them carry weights up a grid. And the idea, again, is to take them to their maximum resistance capacity with repetitions of exercises at increasing that are increasingly demanding. We can, at sacrifice, collect samples from these mice and analyze them by X-ray tomography, where we have a micrometer resolution on the structure, on the microarchitecture of the bone, and therefore we can characterize the microarchitecture of the spongy part of the bone, the trabecular bone, and of the compact part of the bone, so the cortical bone. And so if we look at the trabecular part, which is this distal part here of the femur, for example, then we can see that, as expected, please just look at the black bars initially, that if this is the starting point just before the mechanical unloading phase, there is a loss of the well-known loss of bone. For example, here the parameter is bone fraction, that develops over the 3 weeks of mechanical unloading. If we now look at the gray bars, so these are the animals that were subjected to the exercise, then we can see that, first of all, they start from a better point, and that is also expected and known. And over the first week of mechanical unloading, they don't seem to lose much. And they are much better compared to the ones that didn't exercise, again, not surprisingly. Though over the 3 weeks, eventually they lose the bone as the others. If we look at the cortical bone, so the mid-diaphysis, and we quantify, for example, the cortical thickness, so we can see similarly that there is a better, let's say, quality of cortical bone as well. In terms of the activity of the cells that are responsible for the homeostasis and the renewal of bone tissue, which is something that is continuously going on in the bone, we can see that if we look, for example, at the activity of osteoclasts, the bone resorbing cells, we can see that, again, the black bars, the animals that don't do exercise or special exercise before, during, or after, that we can see that within 7 days there is a huge increase that was known of osteoclastic activity that then kind of stabilizes. And with the mice that were preconditioned by exercise, this increase is much lower, though eventually it also reaches high values. If we look at the bone-forming activities, we can see that in mice, and we see a very quick and important repression of bone-forming activities that are delayed, or mostly because of the starting point are different in the exercise mice. Just one slide on the effects on muscles. For those that are interested, what I can show you for the moment is that, again, the exercise puts the mice at a better baseline level with respect to when the unloading starts. It preserves their muscle quality, quantified here as cross-sectional area of I don't remember which gastrocnemius muscle it was, though eventually by 3 weeks this deteriorates. And we can see this in postural muscles and non-postural muscles. Now, of course, we can do better than that. After all, astronauts don't stay inactive and sedentary while they are in space. So we are now going through the obvious progress of this research project, where we are now continuing the this type of physical exercise also during the mechanical unloading phase, and we are also combining nutritional supplements that from either work in our lab, for example, on nacre powder, or work from other laboratories, has shown some indications that they may be useful to preserve the health of the skeleton, for example, or to fight against muscle atrophy. And the idea here is to reproduce with the mouse model a sequence of phases that mimic what would happen in space, with a space flight, with a pre-flight training phase, with exercise training. Towards the end, the nutritional supplements are introduced, and we have the two phases in red with no exercise that would correspond to the flight to and to the flight back from space, and then again a period when the physical training can take place. And we are also following these animals after the unloading phase, so once they are reloaded and they can walk normally again. And this is because, as you may know, or you may have heard from me yesterday, we are very much interested in following what happens to these animals or to these organisms after once they are reloaded again, and how quickly and how well they recover. So these supplements are ergothioneine, an antioxidant, nacre powder, which is basically calcium carbonate plus some organic compounds that are found in the nacre powder, which comes from the shell of certain oysters, and hydroxymethyl hydroxybutyrate, which again is commercialized, if anything, for its anti-atrophy effects. And I don't have much data to show about that, just to show, again, if you concentrate your attention on the black bars first, you can see that after the 3 weeks, there is this big decrease in bone quality, and this is instead maintained. And please note that this is the post-flight, which is the equivalent of the after 3 weeks of unloading we had before. So in the previous experiment with the Nebula 1, we did not manage to preserve bone quality over the 3 weeks of unloading, and obviously if exercise continues, that helps, and in fact helps pretty well, and we can maintain the quality. So it sounds like a combination of exercise both before and during unloading, together with dietary supplements we use, helps to prevent bone mass and architectural deterioration during the mechanical unloading, with the mechanical unloading associated with this model. And obviously now we are assessing similar protocols where we only have exercise and where we only have nutrition to tease apart the combinations of these. So to conclude, with Nebula 1, we showed that the pre-unloading training delays macrogravity-induced musculoskeletal deterioration. And with Nebula 2, we want to check whether the combined prevention protocol may better preserve bone during and after 3 weeks of microgravity, whereby combined it's continuous exercise and nutritional supplement. So Théo Fauvet is this individual here who has designed and been running the protocol, oscillating between Saint-Étienne and Montpellier. These are the other members of our team in Saint-Étienne, and then many thanks to everyone in Montpellier, Marseille, Bordeaux, and Nancy for this work. Thank you.
Thank you, Mara. We will keep questions till the end, if that's okay, just to make sure we keep to time for the last session this afternoon. So next up is Rebecca Billet de Villemire. Not bad? All right, for an Englishman. Yeah. Rebecca is the head of clinical research at MEDES in France, and she will talk to us today about a project looking at a mobile LBNP, low negative pressure device, moving on hopefully from the static device that we currently have on ISS to a system that's potentially more flexible in terms of operational integration and use in different modalities. So Rebecca.
Thank you very much for this perfect introduction. All right, so I'm going to talk to you about a small pilot study that we made in Toulouse, testing a new device that was developed by a consortium, including MEDES, but also other organizations. So, is it this one? Oh yeah, that's it. Okay, thanks. And then, okay. So yeah, we all know the LBNP device and its use in as a countermeasure. So, of course, what we're looking at is plasma volume loss, post-flight orthostatic intolerance, but also potentially SANS. And if we want to reduce that, LBNP seems like it could work pretty much. But it's at the moment, the biggest problem is that it's fixed to the station. So the astronaut using it can only use it for a certain reduced amount of time every day. And also it necessitates an intervention from other crew members, so it's very time-consuming at the moment. So the project was funded by, sponsored by ESA through a TDE announcement, and then a consortium, French consortium, was created, led by MEDES as project manager and in charge of all scientific background information. System validation, which is what I'm going to present now, and recommendations for the advancement of the project after the validation. CADMOS, which is a part of CNES, was in charge of safety, technical test plan, and spatialization of the device. And then Safran Aerosystems, which is located in Cognac, was in charge of concept and design, manufacturing, development, and technical tests and plans. So this is the prototype. It's very orange. But the main things is that it has to be operated by the user without any external support. So to put it on, to remove it, but also to activate it. It should allow a crew member to move freely within the space habitat, not interfere with daily normal operations, be compatible with modes of exercise, different ones, maybe not all of them, but at least one or two would be nice. It should be worn continuously for several hours, either active or inactive, and be as compact as possible for storage. Requirements were that it should allow a depression up to minus 40 millimeters of mercury. So the pilot study was divided into two sections. There's the physiological part, and then there's the comfort and mobility part. So for the fluid shift assessment, is this, no, oh, sorry, how do I go back? No? Yes, okay. There you go, sorry. So we recruited 7 healthy volunteers, so yeah, small pilot study, but still enough to see how it works and if it works at all. This included 5 males and 2 females, and we were lucky enough to have a wide range of subjects, so they go from 20 to 43 years old, and then their weight is between 55 and 90 kilos, with also big height differences. It goes from 165 to 190. So, and we have 1 prototype. So we were trying to see if different morphologies could work with that device. So for the fluid shift assessment, basically we did LBNP without and with head down tilt of minus 20 degrees. And then we assessed blood pressure with Finopress, stroke volume, ONSD to see if there was any link to intracranial hypertension, and physician surveillance, of course. And then some questionnaires also to see comfort and physiological signs that could appear. This is what it looks like. So this is during the head down tilt phase. So we have the Finopress here. We have ECG and just regular monitoring as well. So this is when the device is activated. And here is the ultrasound for ONSD measurements, which we performed regularly during the session. And then to assess comfort and general acceptability of the device, so we did 2 subgroups. One group would only wear the device for half a day, so that's about 3.5 hours, depending on how long the whole test took. And then the other subgroup with 3 people would wear the device for the whole day, which was 8 hours. So they did all their regular daily activity in there, except they had to remove it to go to the bathroom, of course, but that also sees how easy it is to put on and off. They ate in the device, they're just walking around and working. So we looked at thermal comfort, ease of use, just general acceptability with the point was to target specific areas of improvement for future development of the device and to target specific discomforts and pains. We also checked mobility. So for that, we had a small protocol, I would say, checking walking, biking, and overhead lifts with like a box that you had to put on the shelf. With and without active LBNP. So some areas of improvement have been identified, mostly related to knee joints and the vacuum and control system, which was deemed a bit too big and loud, but we're pretty confident that that can be managed and reduced. And it was perfectly acceptable for 3.5 hours, a bit less so for 8 hours, mostly because of heat. but also because the rigid structure is a bit uncomfortable, especially around the knee joints. So because we had one device and it had to fit all the sizes of all of our subjects, depending on their size, the areas of discomfort were not the same. So it could be knees, but it could also be the waist, because so the point was to have active LBNP on the whole lower half, including the iliac zone. So there was a rigid structure here. And then when you squat down, it kind of goes into your belly. So we just have to improve the ergonomics of that. And then there was an issue with a valve placement that can easily be put on the other side of the pants. Yeah, active LBNP did not modify mobility, but it slightly increased comfort because it creates an airflow, which was best for heat. So here you see a volunteer walking with the device that is inactive. So, I mean, you just walk around normally with it. And then this is a functional mobility test just to check that they can walk fine with it. At the moment, it is active. So, all right, So here is the control box, which is the super loud part that creates the depression. It's also a bit bulky. But yeah, that can easily be improved. And then you have these big cables that manage airflow, and these have to be shortened, of course, because they impede mobility. And then on the waist here, you have like a neoprene skirt, I would say, that ties the device to the waist so that it seals the air to create depression. And this is another part that we should adjust to subject size, because so the device went up to minus 40 millimeters of mercury, except in one female who had a very slight waist, so there were air leaks, and so we only managed minus 30. But I think we just have to maybe create some different sizes, and it should work fine. This is exercise. So as you can see, yeah, the big problem is knee joints, where you can't bend your knee more than that. So that created discomfort during cycling, and bending down to pick up and lift things. Upper mobility is very, yeah, it was adequate. I think it was, we had questionnaires and it was rated at around 9.8 out of 10, so it's perfect. But lower mobility was around 5 out of 10. And it depends on each individual's if they were very flexible. Yeah, thanks. Physiological responses was that, well, the first one is that it is possible to achieve LBNP with a mobile device. And we see that with BP drop and HR increase. So the stroke volume decreased with applied LBNP in the supine position. And of course, it increases when head down tilting. But then how much LBNP do you need to compensate head down tilts? That was extremely variable from one subject to the other. We have a very small population, so we don't know why. And I don't think this is the study to study that. But and then this is optic nerve sheath diameter. So we do see an increase in ONSD with head down tilt, as expected, but LBNP did not change the ONSD. And what we think is that the duration of applied LBNP and head down tilt was too low to get any significant results. But if we could do that for longer, then maybe it would work better. So as a conclusion, yeah, so it can generate negative pressure and maintain it for a few, as long as we want, basically. Ergonomics have been decently maintained, but as I said, there are some areas of improvement. There's a higher inter-individual variability in how they respond to LBNP versus head down tilt. And I'm sure there's plenty of research out there that could be done to test that. It would be very interesting. And then the next step, okay, so next step is automation of the emergency shutdown, because, and this is true not only for LBNP, but for any type of fluid shift countermeasure. If it's a physical fluid shift countermeasure, like artificial gravity or LBNP, the main issue is syncope. So we need to find a way to automate the emergency shutdown of the system. And this, we have been trying to work on that in MEDES, but, and I'm calling to the general community here. If you know how to do that, we would be very interested. And this is the future of fluid shift countermeasures. It's automating emergency shutdown. So either with IA or I don't know, but we have to find out when the body is susceptible to shutting down or going into syncope because of fluid shifts. Yeah, downwards fluid shift. So there was quite a large team with MEDES, but also people from CNES, Safran, and ESA, and I would like to thank all of them. Yeah, especially Anne Pavie and Arnaud Range from ESA, of course, and Jonathan Scott as well. Thank you.
Thank you, Rebecca. Our third speaker, unfortunately, I don't think is here, so we're going to move on to our fourth and final speaker. So our fourth and final speaker is Pierre Baudier, second time, from the Université de Haute-Alsace in France. And Pierre will talk to us about exercise countermeasures in space and the role of physical activity in energy balance regulation. So Pierre, over to you.
Thank you very much. So first of all, I'd like to thank the ESA for letting me the opportunity to present this data, and all of you for staying here until this session. Okay, so as you may all know, the space exploration is still an ongoing story. And we're here today to think about the next phase of the space exploration, which implies longer and longer missions to reach further and further destinations, such as the Moon and Mars, maybe, we hope. The point is, and we discussed a lot about it, that space exploration has a lot of hazards, such as troubles in the vestibular regulation, cardiovascular deconditioning, or musculoskeletal disorders. And among of these points, we have body weight change. We can think that body weight loss could be interesting on Earth, but in space, it's not. Actually, body mass loss can favor all these microgravity-induced adaptations. So we have to work on this point. There is currently a big question for these upcoming missions. We are wondering what is the required amount of food to bring in space. Because we have to find the balance between the medical consideration to optimize the health and the performance of the crew, but also about economic consideration, because it's estimated currently that there is between 2 to 8 €/kg to send in space. So we can easily understand that a slight overestimation of this food will have a major impact of the cost of the mission, while a slight underestimation would jeopardize crew survival and performance. An interesting point, as you can see on this graph, is that the body weight changes are not linked to flight durations. But finally, this body mass loss can only result from an energy imbalance, which means that the energy intakes from the food are lower than the energy expenditure. So now we can wonder who's the guilty. Is there too much expenditure or too low intakes? And by reviewing some data from space mission, it has been observed that body mass loss tended to be negatively associated with the total daily energy expenditure, while no association has been found between daily energy intakes and body mass loss. So we have to focus on this part. And when we are looking data from space mission, it has been observed that the missions requiring a high volume of exercise, such as the LMS mission, led to an energy imbalance in astronauts. On the other side, missions with very low or even light volume of exercise, such as the SLS missions, allowed to maintain a stable energy balance in astronauts. And you may all know that astronauts currently use this device in space to maintain their health and performance. So we made the hypothesis that astronauts' individual body mass and body composition changes are explained by in-flight physical activity-induced energy expenditure, which are not fully compensated by adequate food intakes, leading to the negative energy balance I just mentioned. And that in this idea that my former team, led by Stéphane Blanc and Audrey Bergougnan in France, designed the energy study. This study aiming to understand the regulation of energy balance during long-term spaceflight. So for this study, we recruited 11 male astronauts between 2011 and 2017 from the ESA, NASA, CSA, and JAXA. So about the design, astronauts perform a first 10-day baseline data collection on Earth, and we measure their total daily energy expenditure with a doubly labeled water method, body composition with isotopic dilution, and physical activity pattern with diary logs and 2D accelerometers located on the arm. And after at least 3 months on board the ISS, astronauts perform exactly the same measurements, but in space. Regarding the results, contrary to our hypothesis, no change was observed in physical activity-induced energy expenditure, resting metabolic rate, or even total daily energy expenditure in the whole group in Earth compared to the space collection. However, when we are looking in individual data, we observed a wide inter-individual variability in the change between total daily energy expenditure in space compared to the Earth. So we made 2 groups a posteriori, which will be presented in blue and in red. In blue, we had some astronauts who maintained a stable energy expenditure in space compared to the ground, while in red, we have the other half, fortunately, of astronauts who decreased their energy expenditure in space. So we use these 2 groups to make a posteriori analysis. So here you have the evolution of total energy expenditure on ground compared to the space. And here you have the delta for both groups. And we observed, first of all, an opposite changes, and that the changes in total daily energy expenditure were mainly driven by physical activity-induced energy expenditure, since we did not observe any change in resting metabolic rate. So we have to focus on this part. In the same way, we observed an opposite change in both groups for body composition in the 2 groups. An interesting point is that body mass loss remained almost stable during the flight. However, astronauts who maintain a stable energy expenditure keep maintain a stable fat-free mass in space, but they lost fat mass. And on the other side, astronauts who decrease their energy expenditure in red decrease their fat-free mass because of inactivity, but gain fat mass. So we have totally 2 opposite patterns. So we try to go further in our analysis to better understand the story. And we observed that the changes in energy expenditure were positively associated with changes in fat-free mass, either for total energy expenditure or physical activity-induced energy expenditure, and were negatively associated with fat mass changes. So the more the astronauts remained active, the more they were able to maintain their fat-free mass, but it was to the expense of fat mass loss. So now, regarding physical activity, another surprising result is that astronauts maintain a stable physical activity time in space. It was the same amount of time daily in physical activity. However, we observe major change in physical activity pattern. I mean, that it's quite logic. We observe that astronauts' walking time dropped during the space because of microgravity. However, we observe an increase in running time, mostly due to time spent on the treadmill for the exercise session, and an increase in non-ambulatory activity. This activity, we don't really know what it is. It's all the activities detected by the accelerometer, which are not either walking or running. So it's every daily activities, other training. We don't really know. It's a kind of black box, but here it is. There is an increase in this activity. And an interesting point to keep in mind, because it's of interest, is that the difference in physical activity on ground persists in size, as you can see here for vigorous physical activity and running. Finally, we tried to link all this data together, and we observed that the leanest astronauts in space were also the most active, as you can see on this correlation for overall physical activity, vigorous physical activity, or also time on treadmill. And on the other side, the fattest astronauts were the least active. So basically, we observed that the most active astronauts on Earth were also the fittest and remain the most active and the fittest in space, while the fattest and the least active astronauts on Earth remain the fattest and the least active in space. And last but not least, we tried to derive energy index. And as it has been commonly reported in the literature, astronauts were below energy prescription. That means that they ate less than it was prescribed. So it was logic that astronauts with a stable total energy expenditure in flight were in negative energy balance, which means that their expenditure were higher than index. But astronauts with a lower total energy expenditure in flight were in positive energy balance, which means that even if their index were below the prescription, they still ate too much compared to their expenditure. So we highlighted the non-coupling between physical activity and energy index in space, which is the major concern. So with all this data, where do we go from here? So the first thing is to think about the optimal exercise modality to prescribe to astronauts. We have to think to combine both aerobic and resistive training to improve cardiovascular and musculoskeletal performance, but without induced side effects, such as negative energy balance, as I just explained before, or yesterday we talked about change in brain. So we have to avoid this point. Maybe we can wonder about the time-intensity ratio, for example, the use of high-intensity interval training, or even about the exercise modality, because there is currently some work about the concentric versus eccentric work. So we have to think about it. Another point is that now astronauts have different missions. For example, we have some astronauts performing extravehicular activity for several hours, while others will only do some biology. So they have different needs and need to have a different training. And we also have to take into account individual baseline characteristics. And this consideration will allow us to individualize exercise prescription and food prescription to try to ensure an energy balance. And finally, a very important point, maybe for me the major point to think about, is the need to develop new tools to track in situ markers of energy balance. And it will allow us to maybe to avoid major and chronic energy imbalance, which can compromise health or even performance of the astronauts. And just to quickly conclude, I would like to say warmly my PhD mentors, so Audrey Bergougnan, Stéphane Beur, and Chantal Simon. My team, my former team, unfortunately, in Strasbourg, but also all the people who contributed to this work from the French National Center of Space Research, the CADMOS in Toulouse, MEDES, and also the ESA. Thanks, everyone.
Okay, thank you, Pierre. We have plenty of time for questions. Any of our three speakers. So are there any questions from the audience?
Small room, probably don't need this, but Yeah, the question for the last presentation. I think there was a paper published quite a while ago where they had both ankle and arm accelerometers, and there was a significant difference between the arm and ankle. The legs were not used as much, and so maybe the upper body measurement is not quite indicative of activity in flight. Maybe that if you had two of them, it might have improved some of your measurements.
Yeah. Better. Better. Okay, yeah, you're totally right about this point. I can stand up. The point is, this story is quite old. And when my team planned to perform this study, they only have access to this kind of accelerometer. But I totally agree that today, accelerometer development are improved. We have 3D accelerometer to the arm, the wrist, and the ankle. And I think it could be interesting to combine these different accelerometers to optimize the detection of activities. A point is that we try to overlook this methodological issue with the use of diary logs, where we have information about time spent on each device and some points about their daily activities. And I think we need to combine all this approach to optimize the development of physical activity and daily physical activity, the whole spectrum of physical activity in space. And it could be with the use of different devices.
And I agree with you, and it looks like one of the important parts of the study was that nutrition availability was not the issue in this case. So we're not worried about that as much as you said at the beginning, but going to Gateway, maybe mass is more of a problem. But in this case, what you expected would happen didn't, because everybody was eating enough or more, and so the nutrition side, the energy balance is the important question that you said you were going to try and answer, which I think is a good one.
Yeah, you're totally right. The quantity of food is not an issue currently because we have enough food. The major point is to find how to match, as on Earth, the coupling between intakes and expenditure. Some hypotheses have been made mostly by the group of Martina here in Bonn, in Germany, and by Scott Smith in the USA. Because space environment is CO2 rich, there is some fluid shift towards the head, and the smell and taste could be altered, and maybe also the palatability of food because it's dehydrated. So all these points could contribute to this lack of intakes in space. And we have to find maybe another solution to optimize these food intakes. Maybe to change the environment, the quality of food. We don't really know, but here is the point, because there is this uncoupling. I hope I answer this point. Okay. Thank you.
Yes. I have one more question for you. I don't know if I misunderstood something, but it seems to me that from your data is that the protein catabolism somehow in the space is favored against the fat metabolism. Is that the case, or I misunderstood your experiment? Because it seems like, okay, body takes much easier from the protein from the muscles for getting energy, and just some leave apart a little bit the fat. Is that what can we infer from your experiment, or are you totally wrong?
No, so if I understood well your point, unfortunately we didn't have any data from the protein metabolism in these astronauts. We couldn't get some urine sample or other. But another work has been done in the same study, led by a colleague and friend, Elisa Leroux. We recently published some data about the metabolic flexibility, which is about the use of carbohydrates and lipids compared to what they ate compared to what they use. And the data show a shift towards the use of carbohydrates in the detriment of lipid. So there is also a shift in the use of macronutrients. But today we don't really know if it's because there is a shift in metabolic flexibility or a shift between their food preference. And that's why there is currently a bed-rest study, the BRACE study, which has been led at the beginning of the year in Toulouse, MEDES. And they compared the food preference before and after training. So I hope more data will help us to answer to this point.
Thank you.
But I think the data of Scott Smith in the US investigated the protein metabolism, so there is some point to investigate.
Thanks.
I have a question for Pierre. So yes, so that's why I was raising my hand. I guess what is important, it's obviously the uptake of the food more than the intake of the food. So what is absorbed really by the body, and I assume it's known to what extent it changes in space, if it does or not, and that's maybe also where a lot of the variability can come, given that in space they are forced to eat, I think, maybe a more limited selection of food. So is anything done about that, or can we quantify how much the body actually gets? Because there is something that goes in and something goes out.
Yeah, you're right. That's a good point. I don't really know if there's this data in space. Well, I don't know this data, but it could be done for sure. Maybe we have to ask to Scott Smith or Martina here, because they are nutritional experts and they work in space for a long time. And but I think I read something a long time ago which explains that there was not any difference between the intake and the uptake. So I don't really think it changed. I think the major issue is to trigger the willingness to eat, to give the willingness to consume food. And there was a lot of progress in the last decades to improve the quality, the palatability. They have a lot of choice in their menu. There are astronauts from different nationalities, and we explained in the previous days that they can exchange their food. So, and also, as they have some cargo refueling regularly, they can ask some bonus food, which cannot be stored for a long time. But it's a kind of just a little gift sometimes, and it can promote the food intake.
Yeah, just to comment on that, I don't know if there's any differences in absorption in microgravity versus on Earth, but certainly intake is a problem because for various reasons, food is time consuming in space. You can't just grab a 5-minute snack. Everything has to be open, and there is lots of choice. There's lots of different things you can choose from, but yeah, actually finding the time to eat. Have you ever seen an ISS working day? It's planned to 5-minute intervals, so quite often they will struggle to find time to eat. Digestion is also more of a challenge because of the microgravity. We've had some astronauts report that they prefer not to eat a long time before exercising because of the usual thing, which was kind of magnified in space, so they might almost skip a meal or to try and avoid that. And yes, there's it's prepackaged food. It's not necessarily the most appetizing. It might be in the future for exploration missions that we have to reduce the choice potentially to try and simplify the food system. It might be that we have to move more to freeze-dried foods because of the mass and volume, mass particularly, and they tend to be the foods which aren't necessarily as interesting or nice as the other ones that we have. So yes, I think simply getting food inside people is a challenge. Yeah. So, any further questions?
I'd just like to add a quick point, which is in line with your comment, and I think all of we said during the previous day. It's a beautiful thing in life, but it's more complicated in science, is that there is always a wide individual variability. And everybody is different, has different metabolic, has different food preferences or absorption. And it's quite complicated to anticipate these changes. And that's why it's crucial to find some ways to track in situ these changes. I talked about a lot about energy balance, but it's the same thing from muscle mass or skeletal mass or every changes. We need to optimize this tracking in situ to adapt our modality.
Maybe a question for Mara and Pierre. Starting with your presentation, Mara, if I remember correctly, like with the preconditioning, and then the first study without any countermeasures during flight, you saw that there was, in the end of the unloading, there wasn't really a big difference between the control group and the preconditioning group, and then with the exercise, then you saw that there was a bigger difference. So maybe a philosophical question, like in your opinion, would you then choose to send or make our future crew members more and more fit, like at the highest level that they can be? And then just maybe as an example, with a mission where there's no exercise device, would you then say, okay, we need to make our crew members as fit as possible, as strong as possible, cardiovascular at the highest level? Or would you say they just need to be intermediate, also taking into account that they can do whatever activities they need to do? Or would you, so just one thing was your opinion, but also Pierre's opinion on energy expenditure. Like, what would you choose, or what would you do based on these results?
So maybe it may be worth mentioning also the results from the T-bone studies by Stephen Boyd in Canada on astronauts, where they found that looking at loss of bone in astronauts, the loss was the highest for the ones the astronauts that decreased their daily exercise the most when they were in flight. So this delta of exercise is a risk. So in that sense, it's good to push them up as much as possible when they start, because they start from a better point, let's say. It's like doing a lot of exercise when you are young. It brings up your peak bone mass, and then, okay, you can age. But if then they cannot at all keep that level, maybe that's also deleterious. So I guess it depends on how much they can commit to exercise in space. Yeah.
Yeah, Marat, I want to ask you a question actually about mice and their age and their responsiveness to training. So obviously astronauts vary in age from 30 to 40, 50 and beyond. At those upper levels, obviously those people have been fully through puberty, they've reached peak bone mass, that type of thing. The age of the mice you use, are they young mice in the sense of young people, or are they when you test them, are they in their most responsive period to exercise?
So we choose mice that correspond to the equivalent of adult, kind of young or to middle-aged individuals, humans. It's after the period when they are still growing and attaining their peak bone mass. So we are very careful in the lab when we study adult physiology to study adult mice and not growing mice. We have not done ever a hind limb unloading model, as far as I know, on aged mice. I don't remember now if there are other labs that have done it, but it's something that would be interesting to investigate if the mechanical responsiveness is less in both in the negative and in the positive directions of how more aged animals or humans would respond both to the loss or to the gain in load. And I don't have an answer. But the mice we used were adult, like equivalent. So they were 4 months old, to be specific. And that is corresponding to a 30 to whatever, 40 years old person.
Okay, thanks. Next question. And in terms of the training effect that you get with the preconditioning, is that something you think with a longer period of training you could accentuate? And how different is the exercise they're doing from their habitual exercise before you start the preconditioning program?
So Okay, maybe you should ask Theo to have better answers. So in terms of, how much have we reached the peak level, let's say, through training before, what I remember from the curves, specifically for muscles, was that it seemed that they started to reach a plateau, it seemed so, but after the 3 weeks of pre-training, that we didn't train them longer. So I don't know if that was a slight dip in the curve or if it was really a plateau. And I don't know if Theo has done longer training than that. The second part, sorry, I already forgot.
I was interested in how physically active are mice,
Yeah.
the difference between what mice do normally
Yes.
versus the program
Yes.
that you put
So
them through.
I cannot tell you, numbers of steps or equivalent, but in one of the extra experiments we are running, there are mice that are just normally active, there is a progression in bone mass just because of the aging that comes, but especially in the lab condition, they are not very active.
Yeah, I mean,
And it's true that astronauts are not sedentary people. Yeah.
No, and this is a really interesting point because astronauts are like people. They vary considerably in what they do in their spare time before a mission, and some have certain habits in terms of resistance training. Some have like to run and so on. We do know that the period before a mission is always extremely busy. So we like this idea of preconditioning, use that period to create some sort of buffer. I mean, we don't need that for ISS because we have all the countermeasures in place. But for missions like Gateway in the future, where they're going to be potentially very busy, you're going to have the Orion vehicle with its own device, which we saw yesterday, and then Gateway, which will have its own device. But there is potential there that even though we will very likely give astronauts time to exercise, there will be so many things going on in those missions that are potentially of higher priority in terms of commissioning the station, preparing for the moon landings, that it would be very good to understand if you can create some kind of buffer that would give you maybe a little more flexibility in flight, that if you did have to miss exercise sessions or reduce the total amount of exercise, that you could be confident about what was going to happen to those crew members. But yeah, they are very variable prior to flight. So whether what you see in flight, the variability you see is somehow related to what they're doing pre-flight and what that is relative to what they do in flight. If you're a regular runner before you fly and you use the treadmill in flight, it's probably it's less than your normal locomotion stimulus. So they're a complicated group. So.
Yeah, I just wanted to add a point about what you just said. I think, and we observed it also from different models, a major point is to avoid major change between the habits on Earth and in space. Because, for example, if we use moderately or just a little physically active people and we implement that high volume of exercise, it should enhance these alterations. And it's the same if we take very active individuals and totally suppress their physical activity or food or every other things, it could also create major disturbance. So that's why it's important to study their baseline characteristics. And it's the same, I think, for the mouse and for ill people or every models, to avoid these changes and to have something, a slow transition to guide these changes.
Yeah, I mean, so for astronauts, we can't control what they do prior to flight. I mean, in bed rest studies, I guess it's an interesting example because the people you bring in are selected against certain criteria. Maybe their training history may influence how they respond to bed rest.
Yeah, we do make sure that they are physically active in bed rest study before they enter. However, it's only very recently that we've started tracking their activity, their real activity, not just declared, before they arrive in the facility. And for the last few studies now, we do implement exercise in the BDC period before they start head down tilt. I think that's very important, and it's probably some things that we will be looking at in future bed rest studies is the amount of preconditioning before, and does it actually impact the results.
Thank you. I have a question to you all because, well, energy balance is a quite difficult thing even on Earth. And if you know, when you look at obesity, that if you do interventions just with sports, normally people don't lose weight. Of course, they lose a little bit of fat and they gain muscle. But often, you know, from body weight balance view, it's the same. And it's a quite very tricky thing. So normally you won't lose weight if you just exercise and you don't work on your diet. And we know from W-labeled water and Earth studies very well that when people start doing more exercises, then, well, in the other day's activities, you know, they slow down. They maybe don't do the active more things. They just sit down on the sofa and so on. And I mean, this is much more difficult to monitor in space, of course. But is there data showing something like that, you know, if you go up a bit with the activity, that, you know, other activities might slow down? Is there any studies on that? Do you know if it's the same behavior, or is it, I mean, and I would suggest yes, but is there something where you can monitor? Because this is essential, like if you say, okay, maybe some people should do a little bit more, then maybe they would get less active in the duties they should do, you know, so that's the question.
You point a really good thing, and you're totally right about what you're saying about these compensatory changes in behavior and physical activity and sometimes food, because that's what we observe on Earth. Unfortunately, I don't know. There is no any data looking at physical activity pattern in astronauts, except the one I just presented. It's only one study, in my knowledge, who did it. And that's why it's also important to develop this kind of study to better understand. And another point is that this black box I just presented, which are non-ambulatory activities, we don't really know what it is. On Earth, we can describe its low-intensity activity, moderate to vigorous. It's walking, running, swimming, cycling, etc., etc. But in space, because of the microgravity, we don't have the same algorithm in the space. That's why we can't really describe what it's done. We know they move. It's a different pattern, but we don't know how they move and what kind of activity they do, except when it's logged on their device with running, cycling, and do some musculation, resistive training. So that's a limitation, but I think it's really important to know and maybe to anticipate this kind of change in physical activity pattern as we observe on Earth. Because now we know that it's not the physical inactivity which is dangerous for the Earth, it's really the sedentarity, which are two different components. So maybe we can look better at this point.
Okay, just to follow up, and I agree with what was previously said about nutrition and exercise, because if you look at athletes who spend a long time with high physical activity and then retire, and they don't do as much, but for a while they maintain the same caloric intake, so they gain mass, and maybe that's what's happening with some of these astronauts who have a specific caloric intake, even though it may have reduced in flight. They still maintain that even though their activity has not maintained it. Maybe that's the subcategory that gained fat. And I think it's important, as you say, to measure that before, because some people are habitual at exercise and other ones they do it out of necessity, but given the choice they don't, but they still may maintain the same caloric intake. And I was just thinking about what you're talking about with LBNP and orthostatic tolerance, whether or not you would, as a measure, look at how long someone is standing in a day, because exercise may not be the most important thing in terms of orthostatic tolerance, as we've seen in a number of studies. You exercise and they still faint, even when they're in bed rest. So it may be the same thing, that some people are habitually always standing and are better protected, and that may last longer in spaceflight than ones who do seated exercise, rowing in the supine position, that rather than someone who's waiting tables for 10 hours a day, who's always up they may have more protection because the stressor is gravitation in the vertical axis, not the exercise. So I think maybe what you've all shown us today is it's important to look at the stressor and how that's different in flight and how we can try and maintain that. And I know you with the mice study, I know there were some interesting paradigms where they did nose-up tilt to measure orthostatic reflexes in the mice, whether that might be something that could be done prior to sacrificing if you want to think about that, because you're having them climb up, which also is an orthostatic stressor. You know, if you had a group that didn't do that and just did treadmill, maybe you would find differences in the nose-up tilt. Anyway, some food for thought. And if you have any other things to contribute, that would be great to hear if you have anything else. Thanks.
Just out of curiosity, was there any difference in body temperature between larger and smaller astronauts?
We don't have this data, unfortunately. I know some data which shows that an increase in body temperature in some astronauts during previous missions, but for the energy study, I don't have this data, unfortunately. But it could be a valuable data. But that's it.
Thank you.
Hi. So about the mice, I was thinking, given what you all said, that astronauts are basically people who are among ones who like to move around, right? It's hard to become an astronaut when you don't like to exercise and you're a couch potato. So I was wondering whether, in case of mice, it might be more useful to use, instead of a treadmill, to use a voluntary wheel activity. Because from when I was using these treadmills, I remember that I was always told that it's not quite the natural way of mice to run, because then they are like forced to run faster and faster and faster. So normally when mice run, they would run, take a few seconds of break, and run, and take a few seconds of break, and run. So that's why, I mean, if you, for example, before the forced training, have a group in which you have voluntary wheel activity, and then you can see which mice like to run, because some of them do, some don't. And then maybe use these individuals, so they may deal maybe they resemble astronauts better, and then they may be still forced to exercise on the treadmill, or even to skip the treadmill and just use them in the unloading.
Yes. The thing is, I think it's trying to uncouple and simplify the questions we are asking. So with a given number of mice, we wanted to give the mice the same amount of exercise. But it's true, we could also ask, is there a difference between mice that are willing to do exercise and that are not, and then take the ones that are willing and make them do exercise in a more naturalistic way. In the future probably, but it's for the moment we are in a more simplified kind of exaggerated setup.
So just quickly to go back to body temperature, there was a study on ISS a few years ago with a non-invasive estimate of core temperature using a forehead-mounted device. I'm not a thermal physiologist, so I'm not going to talk about it, but they did detect, or they claimed to detect, some quite significant elevation in body temperature. I don't know about the validity of that system versus a direct measurement. I don't think anyone's ever taken direct core temperature measurements of crew in space, but that's the one study as far as I know. Question for you, Pierre. Talking about energy expenditure and different forms of exercise, you mentioned high-intensity exercise. So looking at high-intensity exercise and sprint interval training, there's lots of different protocols there, different numbers of intervals, different durations of intervals, and so on. Has anyone ever tried to quantify the energy expenditure associated with different protocols? Because on the one hand, it's possible that those protocols could be lower energy expenditure than typical endurance sessions. On the other hand, if you end up with lots of intervals in a particular session, they could be equivalent. So I was kind of interested to know, is that potentially a mode of exercise where we could get the benefits of aerobic training with potentially a lower energy expenditure as well?
Yeah, it was not a space study, but it was with using the same device. A team, an Asian team, I don't remember who. They compared a continuous aerobic training with high-intensity interval training, and they observed that the HIIT session induced a lower energy expenditure, total energy expenditure when you combine the exercise induced, but also the post-exercise oxygen consumption. It was lower in the high-intensity training, so it's a first point. Other studies have shown, mostly in people with obesity, but HIIT training didn't induce an increase in hunger or other. So you won't create a positive energy balance with too much food intake post-exercise. And the last point is also it's less time consuming. Because one thing I didn't mention is that astronauts have 2.5 hours dedicated to training, but in this time you have to consider the time to set up the device, to cleaning, for the data transfer, etc. And finally, they only exercise until 45 minutes per day. So it's much lower, and that's why we have to maybe increase the intensity to optimize the benefits on the different systems.
Yeah, with astronauts, I think there's always this balance between, we want to get the most out of exercise that we can. It is quite time consuming, but also for a lot of astronauts, it's important time for them, because it's the one time a day that we leave them alone. So it's not necessarily, even if it would be nice to be able to find options that potentially could get the same cardiovascular effect for less time. But we always have to consider that for some people, that time is not just about countermeasures exercise. It's really important for them psychologically as well to have some time out from their working day. The same question for jumping. I mean, we talked yesterday about the bed rest study where we seem to get quite promising effects from only 50 jumps per day, so literally 3 to 4 minutes of exercise. Do you know if that type of exercise has ever been quantified in terms of energy expenditure?
I know that also on Earth training, when you compare concentric to exotic training, when you measure the oxygen consumption, it's lower in the exotic training because you only use, you don't voluntarily contract your muscle, but you use the resistance against a higher load. So the oxygen consumption and so the energy expenditure in exotic would be lower compared to the concentric. So I think what Jens presented yesterday could be a promising perspective regarding a muscle stimulus. So also it's another good point for the exotic training and maybe the HIIT training.
Okay, thank you. Any further questions? No? Okay, well, that's the end of our session. Thank you very much. There's a coffee break now, and if everyone can stay around until 4 o'clock for the final wrap-up session, that would be fantastic. Thank you very much to all of our speakers. Thank you for all the questions and the participation. And we will transition seamlessly from nutrition to biscuits. So, thank you very much.